Hey, Mr. P here. In this video, we're going to talk specifically about enzyme inhibition. In the last video, we talked about enzyme functioning and how enzymes play an important role in not only metabolism, but also metabolic pathways that make up your metabolism, which, if you recall, is the sum total of all enzymatic or chemical interactions, chemical reactions in the cell or the body. And so one kind of HL additive or topic is enzyme inhibition. So what happens if or when the enzymes become inhibited, and what are the different types of inhibitors that are going to impact enzyme activity? We're going to get into that a little bit in this video. This should be a relatively short video, but then again, I've said that before, and wasn't always the case. But here we go. There are two types of enzyme inhibitors that we're going to talk about in this video. Both of them are going to impact enzyme activity. Now, the way in which they impact enzyme activity differs, but the goal, if you will, of the inhibitor is the same. It is to impact the enzyme in order to impact the function of that enzyme. The two classes of enzyme inhibitors are competitive and non-competitive. Competitive inhibitors are going to be inhibitors that are directly competing for the active site, and so therefore keep the substrate from binding in the correct location. If you remember from the enzyme activity or the enzyme function video, we talked about substrates being the key to the keyhole, that is the active site, to the lock, that is the enzyme. And so if you were to stick something into the keyhole that is not the key, that substance may in fact fit, but is not going to open the keyhole or open the lock. And so these substances, these inhibitors, are going to be actively competing for the exact same location and therefore interfering with the proper substrate enzyme complex and keeping the proper substrate complex from forming, and therefore inhibiting the enzyme from doing the proper job that it is intended to do. On the other side, non-competitive inhibitors are inhibitors that are not directly competing for the active site. You'll notice that this inhibitor is located in a secondary site. We call that the allosteric site. And you can see it over here. Allosteric site is a site that is almost like a secondary active site. It is a spot on the enzyme that is going to be utilized by inhibitors. And I'd also like to, at this point, say inhibition is not a bad thing. In fact, inhibition often is a good thing, as we're going to get to later in the video. So don't, I guess, up front, before we really get into the nuts and bolts of inhibition, don't assume that these inhibitors are negative. In fact, they are positive in a lot of cases. Okay, so if the inhibitor, in this case, non-competitive inhibitor, is binding to the allosteric site, it's actually going to cause a conformational change or a shift in the enzyme. And so if you see, and it is a slight difference between these two enzymes. These enzymes are, let's just assume, the exact same enzyme. They're the same color, same shape. You'll notice that there is a less pronounced hook on these two edges or the two ends of this enzyme active site. And so the active site should be this particular shape. But over here you'll notice that these actually kind of hook in on both cases, which is going to inhibit or keep that substrate from actually fitting like it should. This is the normal substrate that is normally going to be impacted or acted on by this enzyme, and by adding this non-competitive inhibitor to the allosteric site, we are keeping this substrate from doing its job, or I should say keeping the enzyme from doing its job by catalyzing this substrate, or catalyzing the reaction, because this substrate is no longer able to fit or bind to the active site because of the conformational shift of this particular enzyme. So enzyme changes shape due to the non-competitive inhibitor binding to the allosteric site. It is still a form of inhibition because the substrate enzyme complex is not forming properly. But as you can see between these two diagrams, the types of inhibition are different. Competitive is going to compete for and attach to the exact same binding site, that is the active site, and in non-competitive we're binding to a secondary site, so we are not directly competing for the substrate active site, but both cases are inhibitors because they inhibit the enzyme from forming the substrate enzyme complex. Okay, so they can be inhibited by these two inhibitors, but also remember from the previous lecture that pH, temperature, and substrate concentration, as well as enzyme concentration, can also impact the action of enzymes. Not always, or not assume, don't assume that inhibitors are the only way to impact the action of enzymes, because as you can recall, it is not that case. These inhibitors do impact the reaction or the nature action of enzymes, but it can also be pH, temperature, and substrate concentration as well. Okay, so let's dive into a little more about what competitive inhibition is all about. Competitive inhibition is all about actively binding to the exact same site that the substrate is supposed to bind to. So we are actively competing. Competitive inhibition, the prefix means, or compete, which is kind of the root word of competitive, competing for the location or the binding of the active site, and inhibiting the enzyme action by inhibiting the substrate from binding to it. So the inhibitor is going to specifically bind to the enzyme's active site because it has a similar enough shape or conformation that is going to allow it to bind to the enzyme, but is not the proper substrate, and so therefore the enzyme can't function correctly because it's obviously not functioning the way that it's supposed to. This competitive inhibition, which we can see over here, this enzyme is going to house the inhibitor, which is the regulatory molecule, and regulatory because it is regulating the functioning of this particular enzyme. This regulatory molecule, or this inhibitor, is going to bond to the enzyme and therefore inhibit the proper substrates, which you can see over here. Substrates are kind of this orange molecule and this red molecule. These orange and red molecules, which are the substrates, are going to not be allowed to bond to the enzyme properly, and so therefore inhibited. And it really is that simple. And I know as you look at this bottom diagram, you're probably thinking to yourself that that is obviously a form of non-competitive inhibition, and so I put it here not to throw you off, but to show you something or have something to compare the competitive inhibition to. You'll notice that in this case, this normal substrate is going to take the shape, or this enzyme takes the shape perfectly of this normal substrate, and it's a perfect match. And so this is the normal enzyme action, or is going to lead to the normal enzyme action. If we take this non-competitive inhibitor and we stick it to the allosteric site, notice that it changes the conformational shape of that enzyme, and so therefore inhibits the enzyme because it is not allowed to bond correctly to the substrate. And so this is a form of non-competitive. I put it here just to show you a difference, again, between the competitive and non-competitive. This is obviously the competitive inhibition that we're looking at because it is directly competing for and keeping the substrate from binding. The results of competitive inhibition is that the substrate itself, these molecules, have fewer encounters with the active site and the rate of reaction will decrease. Remember, enzyme substrate specificity and enzyme substrate complex, which is the larger molecule that is formed by the substrate properly bonding to the enzyme, these molecules are not attracted to, per se, this site. They are actually going to just randomly bind based on the collisions from these two molecules in solution. And so we're going to cut down on the number of collisions, or the number of times that these molecules can bind based on just blocking those sites. Okay, so if the substrate has fewer encounters or fewer collisions with the active site correctly, and the rate of reaction will decrease. Okay, that's simple. And a specific example of competitive inhibition in medicine is in a pharmaceutical antabuse, or disulfiram. Disulfiram is a drug that is actually given to patients in the form of a pill that impacts the normal metabolism of ethanol. And ethanol is the type of molecule, or the type of substance that is found in alcoholic beverages and causes a lot of the addiction to that particular drug. And so if a patient is on this particular pill, it's going to competitively inhibit the enzyme that is responsible for changing the acetaldehyde, which is an intermediate product from this metabolic pathway. Now you'll notice from our last video that the metabolic pathway is obviously a series of enzymatic reactions. So we go from ethanol using enzyme number 1 to acetaldehyde, which is an intermediate product, which is going to also be a reactant to enzyme number 2, which is going to catalyze the reaction from acetaldehyde to acetic acid, which is normally a byproduct of alcohol metabolism, if we take the drug, disulfiram, and we utilize its properties of being a competitive inhibitor to this particular enzyme, and the enzyme names are not important. The important thing is to know that competitive inhibition can be utilized for our benefit as we go through kind of this addiction treatment. And if we competitively inhibit this enzyme, we're going to keep acetaldehyde from turning into acetic acid. And the important benefit, I guess, for us as we go through this type of addiction treatment is that when this acetaldehyde builds up in the cells of the patient that is taking this particular prescription, and really if this chemical builds up in anybody, which it doesn't normally do, but if this person takes this particular prescription and this product builds up in the cells of the individual, then the feeling or results, the consequence is extreme nausea, and so therefore it's a deterrent from drinking the alcohol. So if we kind of recap, antibuse, or the disulfiram, is a competitive inhibitor that is competing for and is actively bonding to the enzyme, which is normally responsible of taking acetaldehyde and changing it to acetic acid. Because we are stopping at this point this metabolic pathway, this acetaldehyde is going to build up in the patient, and because it builds up, it's going to bring about the feelings of extreme nausea, which is a deterrent from drinking. As long as the patient takes this prescription, they will feel extremely nauseous when they drink alcohol because of the buildup of acetaldehyde due to the competitive inhibition of this particular enzyme. And so this is a really good thing, but it also has some limitations, because the main limitation to this particular treatment is that the pill has to be taken in order for this to work. So if the pills are, or if the prescription is not taken correctly, then the results are not going to be good, because there are no really deterrents at that point. No nausea is going to come about because of the proper metabolic pathway taking place from start to finish. If we compare that to non-competitive inhibition, you'll notice again from our previous slides that non-competitive, remember, is that addition of an allosteric site to an enzyme. If we bind our non-competitive inhibitor to the allosteric site, we are going to cause a conformational change to the shape, the three-dimensional structure of this enzyme, therefore inhibiting this particular substrate from bonding to our active site, meaning this enzyme is going to become inhibited because the substrate is not allowed to work correctly. These types of interactions can be reversible or irreversible. If we change the conformational shape too much, a lot of times it is irreversible, but most of the time when we add these non-competitive inhibitors to the allosteric site, it causes a temporary change which can become reversible as soon as the non-competitive inhibitor jumps off or is removed. And we'll talk a little bit more about this in a minute. Okay? As long as you know that these molecules are going to temporarily bind to the allosteric site, causing a three-dimensional conformational shift in the structure or the shape of the enzyme, inhibiting the substrate from bonding correctly to the enzyme, making both the enzyme-substrate complex ineffective or impossible, then you have successfully inhibited that enzyme and therefore actively stopped the production of products from the reactants. Let's look really quickly at a graph. The normal enzymatic action in any reaction, when you look at substrate concentration, is going to follow this trend. Okay, it's a positive reaction or a positive slope all the way to a basically maximum amount of energy or a maximum rate of reaction. Notice that reaction rate is going to increase, which is kind of talking about how many enzymes are actually functioning correctly. Reaction rate is going to increase. Substrate concentration is going to increase. Notice that as we increase the amount of substrate an enzyme has to actively act on, our enzymatic rate is going to increase as well, but to a certain point, because it's going to maximum, or it's going to reach kind of maximum productivity. And when it reaches maximum productivity, then obviously the overall slope goes to 0 because we have reached maximum potential. Okay. Now let's look at how competitive and non-competitive inhibitors impact our overall rate of reaction as we increase substrate concentration. As we increase substrate concentration in a competitive inhibitor situation, we're going to increase our rate of reaction slower, okay, or more controlled. It's a slower, kind of less positive slope, okay. This slope, though, is always going to reach the exact same maximum. Why is that important? Because as substrate concentration increases, the rate of reaction also is going to increase like the normal enzymatic reaction, because there are more substrates to act on. However, because we are competing for the active sites, some of the enzymes are going to be inhibited while some are not. So while we actively increase our substrate concentration, some of our enzymes cannot work correctly or can't work at all, and so they are not going to be able to catalyze the reactions as fast, and you'll see that by kind of lowering the maximum potential energy as we get to maximum. But maximum is always achieved because eventually all of the substrate or all of the enzymes are going to work once you get it completely saturated with a high enough concentration of substrate. If you are to compare that with non-competitive inhibition, the non-competitive inhibitors are going to cause the enzymes to actually stop working, and because we are changing the shape of the enzyme and inhibiting, you're not going to release the inhibitor from the enzyme, therefore rendering several of the enzymes useless. And because those inhibitors stay attached or often change the enzyme shape irreversibly, you will never achieve the same maximum potential energy because you have changed or altered the amount of enzymes that are possible. Okay, so it follows the same shape as we increase substrate concentration, but the number of functional enzymes decreases. So we have a limited number of functional enzymes available. So we have dropped this overall kind of maximum potential yield down to whatever level of enzymes we have left. Last thing we're going to talk about is end product inhibition, which is basically taking this competitive or non-competitive inhibition and kind of adding it to what we already know of metabolic processes or metabolic pathways, and looking at how metabolic pathways as a whole can be impacted by non-competitive inhibition. So this is a rendering or a diagram to show you kind of what an enzymatic activity or a metabolic process looks like. You've seen diagrams that are similar to this. You'll notice that there is an enzyme that is going to bond to a normal substrate. This substrate is going to bond to the enzyme's active site. It's going to create an enzyme substrate complex. This complex is going to cause this enzyme, okay, this is enzyme number 1, the enzyme is going to change this substrate into an intermediate substrate A. Then you have enzyme number 2, which is going to bond to enzyme or that intermediate substrate A, and is going to change it to intermediate substrate B. As soon as intermediate substrate B is produced, it's going to bond to enzyme 3, causing your end product. This is a metabolic pathway from reactant to product. As soon as this end product is produced, it can, if it is in enough concentration, say we already have tons of these end products already stored in the cell, and the cell is telling your metabolic pathways or your metabolism that it does not need any more. In fact, it's wasting energy. The body and the cell knows that it is wasting energy. It doesn't need to keep making these because we already have a year's supply of this end product, or a large portion of this end product already produced. It's going to cause this end product to inhibit this enzyme, which is the same enzyme here, and therefore inhibiting the start of this metabolic pathway so that this end product is not produced until this store starts working its way down. The body kind of keeps using it, and all of a sudden it sees that we need some of it, or we haven't been producing it because this enzyme has been inhibited. This inhibitor is going to pop off. It's going to cause, again, the substrate to bind to the enzyme, causing the chain of reactions to produce the end product from this metabolic pathway, causing, again, us to regain stores, or proper amounts of that end product, again, until at which point it reaches a high enough level and inhibits that pathway again. The benefit of this particular process, end product inhibition, is that we can conserve energy and we can conserve end products until we absolutely need them. And so we're going to just produce, or it helps to ensure that we're just going to produce the things that we need at the time we need them. If we don't need them and we have enough, then we're going to turn our enzymes off. The only way to properly inhibit too much end product is by doing a pathway similar to this. We're inhibiting using non-competitive inhibition, using the end product as the inhibitor. End product inhibition. And that was the end of class, and I think that's where we're going to end it. If you have questions, bring them to class. We'll see you later. Bye.